Hi everybody, welcome to part 3. At the beginning of this video, what we're going to start out with is testing our newly rebuilt power supply board. You want to make sure all your new capacitors are still capacitating. You want to make sure that your Zener diodes don't have Zenarial disease. That's a thing. You don't practice safe solder, things happen, you know what I mean? But anyway, so the first thing you got to do if you want to check your voltages is you refer to the schematics, of course. And when I started looking at this, I noticed some things just weren't right. And the more I looked at it, the more things I found that were not right. So let's go over those. Starting over here, you can see at the base of the negative power supply transistor and the base of the positive power supply transistors, the bases are tied directly to ground. Yet they show, this one shows negative 37.5 volts and this is positive 37.5 volts. Well, of course you can't have that if these are tied to ground. And if you look at the circuit, that would really not make sense. So what we need to do is we need to remove these wires. These are not correct. So from here to here and from here to here, those should not be there. That's not correct. Moving along, here's your windings coming in. So your center tap of your transformer winding is here, and then the outer parts of the windings come in J802 and J801. Goes through a full wave bridge rectifier. The negative goes into the negative supply, the positive goes into the positive supply, and it's showing that you're getting somewhere around 40.2 volts here and negative 42.6 here, which kind of is a little bit strange that they would be imbalanced like that, but maybe they are because of the loading on them. I don't know. It just doesn't make sense though. But more concerning is I see 40.2 volts here. If you follow this line, it connects over to here to the collector of that transistor that was on the heat sink from our last video. But right there it's showing 26.2 volts. So how can it be 40.2 on this side and 26.2 on this side, and there's a direct wire connecting them? So obviously there's a problem here, so we'll get into that in a minute. In addition to that, there's a standard diode. So here you have a Zener diode, or Zener diode, however you want to pronounce it. I won't judge you. And we have what looks like a standard diode here, but if you look up Q809, it is in fact a 14 volt Zener diode. So it's drawn incorrectly. The other thing is it's connected right here on this, before this resistor going into the base of the transistor. This is not normally how you would do a voltage regulator circuit. You would typically see this Zener diode on the base of the transistor. So I think they really meant to have this diode over here. Because of course if you had a 14 volt Zener, you can't have 26.2 volts and you surely can't have 40.2 volts. So something's got to give along here, doesn't it? And I think that would cause this to get Zenarial disease very quickly. So we need to move this over here. In addition, there's a 470 microfarad capacitor at 16 volts on a 40.2 volt line, or 26.2 volt, however you want to look at it. So this would very rapidly swell up and pop. So that can't be there either. This is actually the filter capacitor that should be over here. So we need to kind of rearrange the furniture here on this one. And when I went to the board, I actually did some static tests with my ohm meter, and I found that right here in this line there is actually a 150 ohm 5 watt resistor in here, and it's not, they omitted it in the schematic. It's missing. And we can see that because if we go over to here, you see that big white ceramic resistor? On one end, it connects to the center tap of this dual diode pack. On the other end, it connects directly to the collector of that transistor on the heatsink that we did in the last video. So sure enough, that's where our problem is. So we need to draw that in as well. So suffice it to say, there's quite a few typographical errors on this schematic, and we could scribble on the schematic and make notes, but what I decided to do was I loaded this up onto Paint Shop and I fixed it as best I could. So let's take a look at the revised schematic. Alright, this looks a lot better. So first of all, these incorrect wires have been removed, and now this makes a lot more sense the way it is. So you have your 40.9 volts going in, and it goes through this 820 ohm resistor and this other 820 ohm resistor, and now it's down to negative 37.5. So all of this makes more sense drawn this way. Over here we drew in the 150 ohm 5 watt resistor, and we removed the capacitor over here and put it on this side where it belongs. So now this capacitor can capacitate properly. And we moved this Zener diode from over here to over here where it belongs. So it is much less likely to get Zenarial disease. So now we have an anatomically correct schematic. And now we can go in and do our tests and power this thing up and make sure that I didn't make any mistakes. Now there's one more thing, almost forgot. If you notice, these 3 capacitors are circled in blue. And the reason I did that is I got a comment. Someone was a little bit confused because I was moving along pretty quickly and thought that one of the capacitors I replaced was the incorrect value. That it was and it did concern me because I do things like that. Sometimes it happens. You know, you have all your capacitors into the box, and you reach into the bag, you pull the wrong one out and throw it in there. It can happen. So I went back and I checked, and no, they're all correct. And I went, let's pull out the old ones that we have. So we have, this one is 330 microfarads at 63 volts, which is this one up here. This one is 470 microfarads at 63 volts, which is this one down here. And this one is 330 microfarads at 50 volts, and that's this one down here. So they are correct, and these were the correct capacitors, or the original ones that came with the unit. I could tell they were still had the glue on them. They were the same manufacturer and everything. So I'm relatively confident that we got the right caps in there. So just to show you. Okay, let's now move over to our power supply and apply some power to it and see if it works. Alright, I think I have everything in shot here. So I found the common ground point, and I connected the negative probe to that. We got our meter out, have our schematic out, and I have the current limiter set to the 40 watt bulb right now, so we can't overload anything, because you never know, if you get a capacitor in backwards or something, it can short out. That bulb will save you. So the first thing we just want to look at is these voltages here. So we want to see our positive and negative, what is it, 40 volts or so. And it's going to be low because of that bulb limiter that's in there. So it'll be a few volts low. So we should see somewhere in the 30 to 35 volt range here and here, positive and negative. And then up here, they're calling for, it doesn't say, right here on this side of this 330 ohm resistor, they have 35 volts. So you're probably going to see something in that 40 volt range here too. And our 3 diode packs are up here, and we're going to check the center pin of each one. We're just looking for rough estimates of the voltage to make sure they're there and that they're in line with what they should be. So let's turn the power on and see what the bulb does. Oh, do you see a little flash over there? And then it went really dim. It's lit, and the relay pulled in. That's good too. So let's check the center taps of these diode packs. So there's 36 volts. There's minus 37 volts. And there's a positive 30 volts. So that's really good because all 3 of those supplies are in range with what the schematic says they should be, if you take into consideration that you have the dim bulb tester in line with it. Now here's that big 5 watt 150 ohm resistor. So we should see that on one side, we should see that voltage, which is right here, which is your 36 volts, your positive 36, which is going to be, you know, up over 40 volts roughly with full power. And then if we go to the other side of the resistor, 23.9, so it's dropping the voltage. So that's very good. Now we're going to have to get down a little bit lower to get onto the transistor, or to get onto one of the outputs. We have to get on this J809 to check to see if we have our regulated 20 volts. So give me a second to find that and connect the probe. Okay, let's start out with our plus and minus 20 volts. So plus 20 volts is right here, minus 20 volts is right here. You can see them. And those are these 2 pins over here, I'm pretty sure. So we have plus 18.6. We're still on the dim bulb tester as well, so it's going to be low. And minus 17.6, so that's pretty close. Then if the 13.3 volt supply, which was that big transistor on the heat sink that we cleaned up, we'll check that, and that is 13.1. Well, all the power supplies look to be in order, and I think we're going to be okay. We could just check the big one here and see what we get. There's minus 41, plus 41, and of course we'll get the same on this side. These are dual power supplies, so very good. So this is, everything's looking good. We didn't make any mistakes on our power supply board, which is good news. And now we can move on to our power amplifier. Okay, let's get started on this board here. Take it apart, and there's only 10 capacitors on this one, so it'll be easy to recap. But I do want to check and clean and re-grease all of these heat sinks with these big transistors on it, because we want to make sure that they're properly thermally coupled to the heat sinks, as we talked about earlier. So this should be pretty straightforward. And then once we do the board, we'll flip it over and we'll do the big output transistors on the other side. And those are really high quality transistors. I don't see any reason to replace them. Matter of fact, I'm not going to replace any of the transistors on this if they're not having any problems. They're not, unless something went wrong, chances are they're going to be okay, because none of these are the ones that, at least that I'm aware of, that have problems, with getting noisy or shorting out or leaking or whatever. So these are good quality transistors, and I just don't see a reason to replace them. Put something in there that might be different, or that, And just one of my habits is, if I do have to replace a transistor on one side, and I'm going to use a substitute instead of a direct replacement, same one. I'll replace all of them so that at least they're all the same transistor on both sides. It's just kind of a thing I do. I'm sure there's others who, I mean, technically you could just put a transistor in there and it would work, I'm sure, as long as it has the right specs, but I like them to kind of, guess that's just my OCD, huh? Alright. Now you have to be careful removing these. These are those STV, and these are stabistors, and we talked about a stabistor. Am I saying that right? I don't know. But what's in these things, I'll lift this up. What's in these things is 3 diodes in series. And a lot of people say that you can just take 3 1N4148s and wire them in series, but really that does not work. And I got into some detail on that on a couple other videos. A lot of it has to do with the temperature and voltage coefficients. So like as you put more current, as you put more forward current through these, they change, the VBE will change on them, and there's a certain curve to that, and different diodes have different curves. And because these are supposed to be temperature and current regulated devices, the way they're in the schematic, they're actually what does the thermal tracking for the bias. If you use diodes that have different characteristics than these, then what will happen is they won't track in the same manner. They'll work most of the time, but in certain instances the bias will not stay right on. So that's why you have to get diodes that have very similar characteristics to these, and there are such ones, and I got into that in some other videos, so if you want to check that out. And I think the folks over at Audio Karma have gotten into that also, so you could check. I think they have some articles there possibly. But let's clean these up. You just have to watch, because you can't get these anymore. So if you break them, you break these tiny little leads here, you're going to have to make some aftermarket ones, and they're a little bit of a hassle. I do have some solutions for some surface mount ones with these little adapter boards I have, and in a pinch we can use those too, but I would rather have the correct part in there that belongs in there. Again, these don't go bad very often. Sometimes they do, but very rarely. So as long as you don't break them and don't stress them, leave them in there, you'll be okay. Alright, now that we have this up, I'm going to start by doing these transistors. And then as I remove these transistors from the board, we can go ahead and clean around the area there, get the, get the dust out and everything. Alright, reposition the camera a little bit, get a little better view. Okay, this one's all done. I'm going to leave it out for right now. I'm going to pull this cap, and we're going to replace it. So, clean up. We're just going to do a little area at a time is all we're going to do. Make it a lot easier. I can see what I'm doing. You know, I have a cousin that had cataracts. He had pretty bad eyes like me, needed glasses and everything. And he got those implants, those lens implants in his eyes. And I'll tell you what, he said he's never seen so well in his life. He's got 20/20 vision, everything's clear and bright. And I'll tell you, my nephew got the laser keratotomy surgery, the LASIK or whatever you want to call it. And it worked out well for him, but of course he's a lot younger, and I have multifocal lenses, of course. And I don't know, I'm kind of thinking about it. I don't want to get the lens implants until I really need them, so I don't have to have it done again any more often than I need it. But honestly, after seeing what my cousin, the success he had, I'm kind of excited about getting it done eventually. So we'll see. Yeah, there's some crud in there. Let's clean it off a little bit. Just use some alcohol. See if I can shoot the alcohol across the room. All right. The beauty of doing this just for leisure and for a hobby is that you're not pinched for time, and you can do things the way you want to do them and not worry about it. And that's a pretty good idea. Now, I always look at these transistors, because if I see that really bad tarnish on the leads that's creeping up the leads, I call it creeping doom, I'll replace the transistor, because sometimes that will cause that shot noise in the transistors. But these ones are all pretty clean. I mean, they have a little bit of that crud on them, but not, not terrible. I would expect to have that with something that's 40 years old, but I don't really think they're going to go like some of those 2SA726s and some of those other types out there do. But these Marantz ones, like I said, I'm not somebody that works on this every day like some people that do this for a living, but from what I see of these, they don't really need a whole lot of just wholesale replacement of the transistors. Alright, this is a 35 volt 10 microfarad, and I do not have any 10s at 35s, but I do have these little 10s at 50, which will be just fine. And we're going to use KT series, which are pretty good for this application. I think they'll be fine. They're a 105 degree component. Snip the leads here, get them down to length, and we'll solder it in. Okay, and now we can put this one in. Y'all seeing me here? Okay, good. Trying to stay in camera and still be able to see what I'm doing. Bend these leads a little bit so they're lined up a little closer. There we go. Just like that. And then we're going to go over here and just put the little bend on them again. Just like that. And then solder these on. And I will probably fold them back over a little bit. Not real hard like they had them, but just because there is stress on them. See that? So we're going to bend this way, this way, and this one this way, if I don't keep slipping off of it with these pliers. Okay. And there we go. Alright, so let's look. We're going to replace this capacitor down here now. Let me move the camera because I'm working here towards the edge a lot. I'm not getting everything in frame. So how's that? Of course, now I'm going to hit my head on it, but that'll be extra entertainment for you. No extra charge, huh? All right. So this is the input capacitor to the power amplifier board. So this is actually where your audio is going to come into the board from the preamp and from the tone, from the line stage and all that. And this again is one of those orange with the epoxy seal on the bottom, one of these low leakage current capacitors. 2.2 microfarads. Now the small ones that are like 4.7 mics and below, we can use these film capacitors, and these are really good. They last forever. They actually are lower leakage than these. They're better in every way. The only problem you run into is as you get larger, like for instance, this is a 100 microfarad capacitor, and it's one of those low leakage current ones as well. But a 100 microfarad film capacitor would be massive. It just wouldn't fit on there, so it's not practical. And that's where we would use our KL series Nichicons. I think somebody mentioned an Elna brand that was listed as a low leakage current as well. And that could very well be. Elna capacitors are very, very high quality, but I've not found them to be really super available. Some of those Elnas are no longer being made. So I don't know if they're current production or if it would be like a new old stock for that one that was mentioned. And I wish I remember which one he mentioned on the comment. But I'm always interested in knowing other sources of, you know, good quality components like that. So here we go. I had to bend those leads in just a little bit because they're just a little bit wider than the leads on the original cap. You don't want to force them in, you know, into the board, or it could damage the capacitor where the leads go in. So bend them with your pliers. People ask sometimes, why do you clip the leads before you solder them in? I don't always, but I try to make a habit of it. When you solder it now, the solder will actually go into the end of the lead. And what do I mean by that? Well, when you look at these leads, they're copper, but they're that silver color, and they actually have a silver coating on them, even on the end. And that prevents that copper from turning green and corroding. Theoretically, if you solder these in and then cut the lead off at the end, that copper at the end will be exposed, which could theoretically allow ingress of moisture or whatever to allow it to corrode through the lead. Now, it's very rare that I've ever seen that happen, but I guess it is possible, and it does make for a much neater soldering job, as you can see over here, when you do it that way. So I just try to get in the habit of doing that. I figure if it doesn't make it any worse, and at best it will make it better, why not do it? Okay, that's done. Let's go down and do this one here, and then we'll work our way up over to here. Okay, that one's done. Now we're going to do this capacitor here. It's just easier to do those heat sinks off camera because I have to be able to get it up to where I can see it. It's just so difficult. And they bend those over so badly. And of course the one thing bad about these is they go to sleep, and I know I could set the sleep time on them, but I really do need to get in there and change the sleep time on it because it just seems to fall asleep too quickly. And then you have to wait for it to warm back up. But the sleep mode on these Heikos is pretty good because the tips last a really, really long time, because they cool down when the thing's idle. All right, so this is a 10 microfarads at 16 volts. And I think I have one of those here. Yep, 10 at 16, there's the new one. Let's put it in. And attach it. Like I said, I don't know how I'm going to edit this video, if I'm going to let some of this in there or what we're going to do. We'll see. Somebody had made a comment. I made a comment about that I really don't share a lot of my day job I don't do a lot of videos on X-ray and so forth because of the manufacturers, and somebody brought it up that yes, there are in fact videos of people doing service or repairs or show and tells on X-ray equipment on YouTube, and that is very true. But it's really not something that I'm interested in getting into, especially with my vendors and everything that I deal with. I would rather, and I've put some things out there for you guys on my channel a little bit. Just can't put everything out there. And I have a couple clips that later on I want to do some more on my X-ray series, but it's kind of tough to do, to get the time to do it, because it's a lot of editing and things like that. So one of these days we will. All right, let's pull this heat sink. This one, and I'll tell you, the problem with this is they fold these over so much. I think I'm going to reflow these before I try to remove them, and then I think I'm going to use the solder wick on these instead of the desoldering gun. And yes, I know I'm bridging them together. I don't really care, because I'm just going to be removing them. There's 2 transistors on this one heat sink, so we'll have to remove them together. Let's see if I can use a little bit thicker solder braid that'd be a little faster pulling this stuff up. You all see what I'm doing here? All right, let's see how this works. Like I said, I know why they bent the tabs over. They want a good mechanical connection in here as well, but it really makes it hard to get it cleaned off. That looks pretty good. Just so bent over. And you probably could get away with not servicing these heat sinks and regreasing, but I don't like that, because these fail. And a lot of people think it's just because they're old style transistors, but actually these were very, very high quality transistors in their day. They fail because of heat. And if you keep them cool, they last a really long time. And you typically don't have to worry about replacing them. But you have to make sure they're on there. And it's funny, because I've noticed even with the Pioneer gear and the Sansui gear that use these onboard heat sinks like this, they do a really good job with the thermal compound and everything on the big output transistors, but these little ones on the board, they get really, really hot. And a lot of times they don't really do a good job of thermally coupling them. And I've seen a lot of them where the screws had worked loose over the years to the point where you could unscrew the screws with your fingers. You didn't even need a screwdriver. And I believe that's what causes those to fail. And a lot of it is the thermal cycling, getting hot and cool, and it'll loosen those screws. And then if it stays like that for years, it's not even really coupled to the heatsink. And you end up, damaging the transistor. So I think they get a bad rap, but they really don't deserve it, because, again, it's not the transistor, it's the way they're mounted. All right, that came off better. I think that's what we're going to use from now on to get these off. We were able to get in there. I don't know if I stayed in camera or not. I hope I did. And get all this glue stuff out of here. I don't know if it's glue or if it's just flux. That looks more like flux that's getting up, through the holes here from the bottom of the board and just getting all crusty. Okay, I just clean these off a little bit. So same routine with these, and I'll clean them up, replace the grease, clean the heatsink, and we'll put it back down. Alright, one down, one to go. This side is finished, and now we're going to do the same thing to this side. Get them all cleaned up, and this amp will be ready to test. And when we put this back in, we're going to give the whole receiver another test to make sure everything's working. Okay, the heat sinks are all done. We're down to just doing the capacitors. So let's get those replaced. If it's warmed up yet or not. You know, last video I did that little skit, you know, I lost my flux cleaning brush. It disappeared. Actually, it was under the chassis of the receiver. I just couldn't find it. And I made that little joke about the pet shop scene from Monty Python, where the guy has the dead parrot in the cage and they're arguing back and forth, you know. Your parrot is no more. I thought that was funny. I saw that years ago. I don't know what made me think of that, but and then I got to thinking about it. It reminds me also of that movie Monty Python and the Holy Grail. Remember the scene with the Black Knight? I cut your arm off. No, you didn't. You know, back and forth. Merely a flesh wound. Same kind of argument. It's pretty cool how they kind of use that same theme for a couple of their skits. What made me think of all that to put it all together? I got too much time on my hands right now, huh? I don't know. So let's replace this. You know, come to think of it, that's kind of the way we are with capacitors, isn't it? Yeah. You're leaky. No, I'm not. Yes, you are. You're leaky. It's just a trickle. I'm not leaky. You, of course, are leaky. I've tested you on my leakage meter. I have a big red light bulb that lights up when you leak, and you are leaky. I'm not leaky. I've been doing this for 742 years before capacitors were even invented. You're leaky, and I know it. I play my Pavarotti records on you, and he sounds like Tiny Tim. No, he doesn't. You're just a capacitor snob. You're just one of those audiophiles. No, I'm not. I use science. Let's get on with this. Yeah, cut to the chase. All right. I've lost my mind. But you got to think about it. That now that I think of it, it does kind of remind you of that, doesn't it? Some of the arguments we hear out there. Uh-oh, what's that clicking sound I'm hearing? It sounds like the sounds of people clicking the unsubscribe button. Oh well. That's what you get when you watch my channel. Sorry. Some of you might get some of that. And if not, it'll give you something to look up. We like Googling things and YouTubing things. Let's put this one on. Can you still even see? Am I even on frame? Yes, I am. Okay. All right. And again, this is the input capacitor to the amplifier. And this one, since it's only 2.2 microfarads, I'm able to use a film cap, which will pretty much work. You know, we won't have any problems with it, and it will perform very well. You notice even it's only slightly larger than this, but it still is kind of a tight fit. You kind of have to tip it a little bit. And if you notice this heat shrink here, I didn't mention this on the other side, but there are two transistors sandwiched together in there. So it's funny that in the tone control amplifier, they use those dual transistor packages that I talked about in the last video. But in this one, they made homemade ones by taking 2 matched transistors, and I'm sure they matched them, and then heat shrinking them together so they thermally couple. That helps this differential pair to track. And then one of these transistors, it's either this one or this one, acts, I think, as a current source for the long tail pair. But anyway, getting in, you know, extra stuff. Okay, let's replace this one. This is another one of those orange low leakage. Now everybody's going to be teasing me about the capacitors. Maybe I shouldn't have said all that. Yeah. Okay. Looks good. Let's clean this off a little bit before we solder on it. What is this? This is that 100 microfarad. And I have a replacement KL series 100 microfarad 16 volt. And you know, I want to go back through the comments on the last video because somebody mentioned a one of the Elna brand capacitors that was also supposed to be a low leakage current. And I'd love to know if they're still currently being manufactured or not, because that would be another good brand that we could try for the, you know, in place of these orange capacitors. And I have, like I said, I have used the Nichicon Fine Golds, and you know, they sound good to me. Of course, like I said, I'm not as critical of a listener when it comes to that stuff, but it seems to function in the circuit, and you know, they sound good to me and seem to be working just fine. But realistically, if you look at the specs of those old orange capacitors, they are most closely related to the modern low leakage current capacitors. Okay, let's replace this one. This is the 10 microfarad at what, 10 at 35. Okay, so we'll replace that, and that's just a standard cap. Kind of hard to hold this thing at an angle like this. I have the camera kind of situated above it, and I'm off to the side so you can see a little better. And that cap just went flying across the floor. You know, I'm almost thinking of getting some sort of a white vinyl smooth floor mat of some sort that's white, so you could see components when they fall, and even have a little lip around it that kind of like tips up, almost like those mud mats or whatever they call them, so that when these things go flying, I don't have to go on a search to find them. Because I'll tell you, that takes up more time than anything else. All right. Put this one in. I actually like some of the old British comedy from the 70s and 80s. A show I used to watch called Keeping Up Appearances, and another one called Are You Being Served? Some of you may remember those. They were, I think they were 1970s, 1980s comedy, but really funny stuff. Just craziness, you know. Drinking my coffee here too. Yeah, I like that because it's different than some of the other stuff you see. And you don't see things like that anymore as much. That's why I don't watch TV too much anymore, because it's just that kind of stuff's gone. And a lot of stuff today, I don't know, just the humor, I'm not interested in it. It's not witty. You don't. I like humor that, you know, a minute or two after you hear it, then you laugh, because it doesn't hit you right away. To me, that having that delayed reaction makes it even more amusing. I don't know. Why are we talking about comedy? I don't know. This cap is right here. Okay. And I'm going to hold on to this one so it doesn't fall on the floor again. Okay. And that is another 10 microfarad. It is. And it was at 16 volts. Okay. And I kind of try to bend the pads in the direction of the track. Or I mean bend the leads in the direction of the track, so they kind of hang over that way. I don't know why I do it. I guess it's a little more steady that way, and then the leads don't bend over top of other things. Who knows? May not matter. Or maybe it's not the way to do it, but that's how I've always done it. Okay. A lot of these older units will use you can see this, they'll use like a different type of heatsink grease. It'll be more like an oily type thing, and it's clear. This doesn't look like that because it's kind of that yellowish color. But that's actually pretty good stuff, and it lasts a very long time. But again, you just don't know what, you know, if it's dried out or anything. So I like to redo them. It makes a difference. These transistors will heat up very quickly when you put a low impedance load on them and start running high volumes, because they will start having to deliver very high current, and they have to dissipate whatever current isn't absorbed by the, you know, by the your load, your speakers, is going to be absorbed by these, and that's hence the heat sink. And it can change temperatures very rapidly, and you want that temperature to wick off into the heatsink as quickly as possible. So the better thermal coupling you get to this, the more efficient it'll be at doing that. So that's kind of my theory behind why I always clean these off and re-grease them. I can tell these have never been removed in the 40 years they've been in existence, because the green enamel paint that, you know, that they put on there, you can see is still there. You know, we're just breaking that seal for the first time. So that's a good sign that nobody's been in here, nobody's messed with it. I mean, this has been a good receiver to restore, because it's not been worked on, and it has not been used heavily. And I mean, that's the best of both worlds there. That's the perfect type of receiver you want. If you want one of these that you're going to restore to be able to use and listen to it the way that it was intended when it was built, that's the one you want to get. One that has low hours and that nobody has worked on before. And again, if it's been serviced by somebody who's a professional, you won't even know it was serviced, other than you'll see a component or two that's been replaced that, you know, may look a little different than the others, but it's the correct one, and it's a newer component, and it's perfectly installed. That's not a problem, but you don't always see that. A lot of times these things were taken, instead of to an authorized service station, they were taken to like a TV shop or something. And not that TV repairmen, you know, that was my cousin and he was fantastic, but a lot of them, because there's not big money in these as compared to how television was back in the day, these kind of got repaired quickly so that they didn't lose money on them, and they didn't always take the time just because of cost constraints, because the customer wouldn't pay to to do a really neat job. A lot of times, especially with the tube gear, you'd see, just cutting leads and tacking things in there and things, which would work. I mean, obviously they worked for a long time, but you didn't always see that. And then you kind of, if you want to really restore this perfectly, you have to kind of reverse all that, which can be a little bit extra work. But I don't blame the technicians that did that, because again, it was a cost versus value thing. Is it worth what somebody's going to pay you for it? And you try to make the right decision for the customer. So it's not that all of these people were hacks or anything like that, but it's really because they had to make some concessions to be cost effective. So remember, these things were not considered valuable antiques back then. They were readily available and you could purchase them new, and if you spend too much money repairing it, it wasn't worth it to them. It's easier to throw it away and buy a new one, although these were made to be repaired. So thankfully they're still around. Okay, so let me get some stuff out here. Okay, for these transistors, I like to use this stuff just in a tub like this silicone. It's still silicone based, it's just in a plastic tub instead of in a tube. And that way I can just get a tiny little bit on one of these brushes and just lightly spread it onto the transistor. And it spreads it better, you use less of it, and it's a little bit neater, I think. Of course, this stuff gets all over everything, but I guess that's how it is. And I'll usually check these mica pads out as well. If they're bad, I'll replace them. But usually they don't go bad. I mean, a mica pad, there's really nothing that can ever go wrong with it unless you bend it and crack it. Which, of course, that can happen, but if you're careful, they hold up. And the nice thing about them is it doesn't matter how much heat you put to them; it doesn't hurt them. Those sill pads, I've seen those sometimes go bad, where if they overheat, they'll get kind of charred a little bit. It takes a lot, but I've seen it happen. So there we go. That's it. Just a nice thin coat. Spread it out. And then you have to, these have those those sockets on the bottom, and those sockets are really nice because it makes it very easy to mount these. Some of them are screwed to the heatsink, and you have to actually put nuts and bolts on the back, and it's really awkward. And these are so much easier. They just plug in, but you do have to hold them. They have these little pins inside, and you see how they're split there, and you have to get it in between those properly in those pins, or it'll get stuck. So if you plug it in there correctly, you'll feel when those pins seat properly. If not, it'll get on the other side of those pins and it'll wedge, and it won't work right. So you have to hold this straight. And if you notice, there's these little shoulders, and they fit inside. They recess up into the heatsink, so the screw is physically isolated from the heatsink as I bang the camera. See that? I don't know if you can see that or not in there, but see how they're in there? When those screws go in there, they will not touch. And the same thing, these holes are big enough that these little pins will not touch. This socket will hold everything centered in there properly. So you just kind of want to feel it, and you should just feel some force plugging it in, but it shouldn't be so hard that you have to bear down on it real hard. And you got it right. And you start these, and you take your screwdriver and you tighten it down. And remember, the case of these transistors is one of the elements. The case is tied to the collector. So that's why we have to stay isolated like this. If you look on the schematic, you'll see that there is voltage being applied to this case. So if you take your meter and you measure from the heatsink, this chassis right here, to this case, you will see a voltage potential there, either positive or negative voltage, depending which side it is. And if this were to touch the heatsink, it would short it out. So when we were talking a little bit about the, as I dropped the screwdriver, when we were talking earlier about that heatsink compound. Now I dropped the microphone. Good Lord. When we were talking about the heatsink compound that's conductive, and yes, there is conductive, and no, not all silver, Arctic silver is conductive. That tube that I showed in that little picture when I made the comment actually specifically said thermally and electrically conductive heatsink compound, and a lot of times they will say that on them if they are electrically conductive. Just something to be aware of. And if in doubt, don't use it unless you know for sure that it's not conductive. But you can see, if some of that stuff were to squish around there and get on the top and on the bottom, it could technically make a path through there. Especially when it gets on the screw and goes through there, it can touch the edges of the heatsink and so forth. But anyway, we talked about that already, so. All right, so that's done. Let's do our next one. By the way, if you notice, when I put this stuff on, I'll get a little dollop of it, and I always start in between the pins in the center. Let me show you why. Here's a TO3 transistor with that top cover removed. And this is not the transistor. This tiny little chip here is the actual transistor element. And you can see it's thermally, they use a thermal glue and they glue it to this base metal plate. And this actually is the heat spreader that spreads the heat out to the heatsink. And if you notice, it's positioned in between the pins. Okay, now this transistor would fail if we put it together right now, because you see these tiny little leads. So the collector is fused to this case, and you notice there's only two wires, and that's the emitter and the base. And those little bonding wires are tiny, and you could see how this sticks up like that. These right now are bent down, and they're actually touching. And you can see now they're not. So now this transistor would work. But that's another thing. If these get dropped and hit really, really hard, I've seen some of these where that's touched that case and shorted out. The other thing that can happen is if you put too much power through these transistors, that little bonding wire will burn open. And that's when you see an open circuit. And sometimes this little wire will then fall down and touch the case, and that's how you'll see a short. And that's how these these transistors fail, among other things, of course. But I just thought you'd think that's interesting. But the reason I spread the heatsink grease in the center, I start at the center of the pins, is because of where this is. The heat, the main hot spot of this transistor is going to be right beneath this, which is kind of in between the pins. So I always start that. That's more important to get a good thin even coating of heatsink grease here than it is out on the ends, and that's why. Thought you'd be interested in that. By the way, that transistor that I showed you was a Chinese one. It was a low-cost one that you can buy on eBay for 50 cents or $1. This is the equivalent to it in a vintage Motorola transistor. Notice the difference of the heat spreader. Notice the difference of the bonding wires, how it's assembled. it is much higher quality. That's the difference between the more expensive transistors, or the vintage ones especially, and the more modern ones that you see that are mass produced very inexpensively. They both will do the same thing, but you just look at the quality of manufacture on these versus that other one, no comparison. Just for the record, these Japanese transistors are extremely high quality that were used on these Marantz receivers. And if you look, notice that little shape there. You see it? If I look at it from an angle, you can see that, see that? It actually stands proud of the base plate a little bit. And what that does is that helps. Remember, on the other transistor I showed you with the top off, you notice it had that heat spreader on the inside that the element was connected to. That's what this is. And since it stands just ever so slightly proud, when you tighten this down, these tabs kind of push down and it forces this center plate tightly against the heatsink to give you the best thermal transfer possible. And that's why it's like that. So again, these are extremely high quality. I don't know, people have gotten into the habit of just wholesale replacing them and thinking that it improves the sound quality or makes it more reliable or something. But that's absolutely not true. These are over-engineered on purpose. And the people that designed these receivers knew what they were doing. Unless there was a problem with the amplifier, it was biased incorrectly or improper load was attached to it or something to damage the transistors, these will last a lifetime. You don't need to replace them, and they're going to perform every bit as well as, you know, a new transistor. They do make good quality transistors still today, but they're not going to improve over what these do. These are the correct component for this design of this circuit. They didn't really worry about cutting corners like that back then, nor did they not have the technology. They had the technology to make good transistors back then, and that's what these are. Just thought you'd like to see that. And there it is. Our module is done. Went together pretty well. All right, we've fitted the power amp board back in. Everything's back together. We're connected to the speaker A terminals and all set up. Hopefully this should work. And we're going to measure the DC offset if the relay comes in. I'm going to start out on low power. And turn it on. Okay, the bulb has gone dim, but I don't think there's quite enough voltage right now in the power supplies for the protect relay to come in. So let's turn it off. Let's go to the next size up in current limiting. And there goes our relay. And our DC offset is settling right down. Look at that. Just a couple of millivolts on both channels. We'll give this a few minutes to make sure it doesn't drift too much, but they look to be holding up pretty well. So I'll watch this for a while and then I'll be back. Okay, both of these are staying really well within where I want them to be, so I'm quite happy, and we're going to move on and check our bias now. Okay, so as you can see, there's 4 little test points right in the middle of the power amp board, and the 2 inner ones are the left and right channel positive, and the outer 2 are the left and right channel negative for your meters. And this is directly where you read your bias. And so it's very simple. You set your meter to millivolts range, and you move it down here, and you can see What they're asking for is 30 millivolts DC. And as you can see, this one's set way down. It's at about half of what it should be. This side's only 15 millivolts. This one's only 13.7, 13.8 millivolts. And the amplifier is sounding pretty good. This is another example of what I'm talking about, is it's under biased right now. And you can tell because this thing's been on for about 10 minutes. And these transistors down here are warm to the touch. They're not burning your hands, but they are warm to the touch. And this side is slightly cooler than this side, and that would make sense because this one's biased a little bit lower than the other side. And the transistors up here on the top, this heatsink, is just absolutely room temperature. It's hardly warm at all. And that's good. That means the amp, if it sits there and idles, it'll just it'll just sit there and stay really cool. Now, I'm going to leave the bias like this. I'm going to set them both to about 15 millivolts, which the one side's already there. And then I'm going to do my tests, and if there's no crossover distortion or anything that we can see at low volumes, I'm not going to bother changing it. I'm going to leave it where it is. Okay, that's pretty good. So we're going to go ahead and leave those where they are, and then we're going to go ahead and put a signal in it and see how it works. Okay, let's turn this thing on. We have it all connected, and I'm going to go to full power, which is good, and it's idling at about 450 milliamps roughly, which is good. Let's turn the signal generator on, and you can see already we only have one channel. Oh well, that gives us something to do, so let's turn it around and see where we're losing it. Okay, now I could go into 3 channels on this, but it started to get kind of noisy. I'm going to use this scope to kind of differentiate what we're looking at from the output. So this scope is showing the output across the dummy load. This scope is showing the input going into the first channel of the amplifier. So I'm going to turn this up, and you can see as I turn it up, it's not synced to that, but you can see I get an output there as I get an input here. And ooh, look at that. The other channel comes in after I turn this up a little way. Huh. So let's connect over here and move the camera a little bit so you can see what I'm doing. There we go. I think you can get everything in view here. And we're going to go to the wiper of the first channel. I'm going to start turning this up and see if we get anything. And I have to turn this down or make the sensitivity a little bit higher. Let's go over to this channel, which I'm going to assume is the good one. Yeah, see, they come up together. Very strange. When I connect this now, I think, yeah, this pot's bad. Okay, so there's a problem with the potentiometer. So I'm going to have to take that apart and look at it. Okay, I am still not happy with this pot. If you recall, when we first tested the amplifier, it was really scratchy, and I figured, well, it just needed a good cleaning, but cleaning it did not help. And I don't think it's ever been cleaned before either, but it just doesn't seem to be making good contact with the wiper. And I keep several of these Alps 50K with the loudness tap. I keep them in stock. So I'm going to just replace it. For what these cost, I'm just going to replace the pot. And this one's actually a lot nicer because it's got a detented knob, and it's brand new, so that'll last forever. They won't ever need another one. And I think this one will be a drop-in replacement. So it looks like the shaft and everything's exactly the same size. So win-win situation all around. Let's see. Nope, it's a little bit bigger shaft if you look. Just slightly bigger, so we'll have to open that up a little bit. No problem. We'll get that mounted up and then we'll try it again. Alright, much better. Now let's get back to our original test. Turn it on. Let's see if that should take care of it. And we're going to see just how much power we get out of this now. Let's see, turn that off. Okay. Zoom in a little bit. Okay. Let's take a look at, down here will be the voltage, and I did not program in the watts calculator, but I know I can do that with this just the way I did with the Tektronix, so I'll just have to do that one of those days. But for right now, we'll just go through and let's take it up till clipping. There's clipping right there. We're just starting to clip, and it's 29.7 volts. Let's call it 29.5 volts because it was just starting to, you could see it cycling a little bit. That was kind of topping out the capacitors on there. So 29.5 squared divided by 8 ohms, 108.78 watts. So 108 watts would be way over the 94 watts that it's rated at. But of course, that's, you know, this is just at a mono, or just a sine wave single tone. But I think that worked out really well. We can do the frequency sweep, and we'll probably do that next, but I'm going to set this. I think everything's good right now. It's all going to work, and I think we'll do the better test at the end of all this. But for right now, I think we have this thing working, and I think this is a good place to stop, and we'll move to the next part. So until then, I wish you all peace, joy, happiness, and good health in your lives. Hope you had fun. I sure did on this part. And we'll see you again real soon, and hopefully in the next clip I will have those boards in that we can do the new filter board. I did get the capacitors, but I do not have the boards that I ordered yet. They're shipped, but they're not going to be here probably for about 4 or 5 more days. So we'll wait for those to come in, and we'll be back with the next part. Till then, take care, and we'll see you soon. Bye-bye.